Welcome to Introduction to Quantum Field Theory, Lecture 18. In this lecture, I will be talking about an application of the things we've learned in previous lectures. Namely, I will be talking about identifying thermal phase transitions. In the previous lectures, we have discussed some of the basics of quantum field theory. In this lecture, I would like to use some of that knowledge that we have gained to a physical problem of interest, namely that of thermal phase transitions. Thermal phase transitions occur in several interesting physical systems. For instance, the QCD phase transitions in the early universe, the electrovake phase transition, and the Higgs mechanisms in particle physics, as well as several other examples in different contexts of physics, such as superconductivity phase transitions. To do a quantitative calculation of the specifics of these various systems, we would need additional tools. We would need to learn about gauge fields and fermions and so on and so forth, which we haven't done so yet. However, we do have the tools to discuss the physics of thermal phase transitions qualitatively using the setup of scalar field theory that we've used so far. In several previous lectures, we've considered quantum field theories with a scalar field that has an interaction potential of the form that is quadratic with a mass and a phi to the 4 term. We set up perturbation theory for these systems, and we had that the expectation value of the field was vanishing, and the expectation value of the two-point function was given by the free Green's function. Higher order correlators were given in terms of products of propagators using Wick's theorem. So what I want to do in this lecture is that I want to consider potentials where I flip the sign of m squared, and instead of considering the potential that we've been using so far, consider a potential that has a minus m squared term here. For any non-vanishing coupling constant lambda, positive non-vanishing coupling constant lambda, the phi to the 4 term will stabilize the potential. So the quantum field theory will still exist because the integrals are still convergent, but the flipping of the sign of m squared has other consequences. To get a feel for the potential, I have included here a plot of the potential for a specific choice of the coupling constant, and it shows that it basically goes down for small values of the field, then has a minimum at some value, and then continues to rise according to the phi 4 term for large values of the field phi. Note that the point phi of 0 is classically unstable. If you a point particle at this point, it would basically roll down the potential. This instability is a consequence of the negative m squared term that we have in our potential. Negative m squared means imaginary mass, and you can use it as a rule of thumb that whenever you have an imaginary mass in the physical system, this always signals an instability of the system. For exactly vanishing coupling constant lambda is 0, the potential is simply completely unstable. The perturbation theory will not work as before. In some sense, if we were to try to set up perturbation theory as we have before, expanding around lambda is 0, we are just expanding around the wrong ground state. It is fairly straightforward to figure out how this situation can be repaired. Instead of expanding around the wrong ground state, we have to expand around the stable minimum of the potential instead of the point phi of 0. Formally, what we can do is we can separate the quantum field phi into a constant phi bar plus fluctuations phi prime of x. We will refer to phi bar, the constant, as the mean field. And if we do so, then our path integral for the partition function becomes a regular integral over the mean field and a path integral over the fluctuations phi prime. Similarly, the action will have two parts. It will have an action that just depends on the mean field and a residual part that depends on the mean field and the fluctuations. The point to realize is that indeed the integration over the mean field is a regular integral rather than a path integral, and that will be important in the following. We can formally perform the integrations over the fluctuations phi prime so that we end up with a representation of the path of the partition function that is the regular integral over the mean field times e to the minus beta v, where v is the volume, times an effective potential Vf that is just a function of the mean field phi bar. As I said before, the term Vf is just the effective potential. And in the large volume or low temperature limit, this integral here gets dominated by the saddle point. So in the limit beta v, either small temperature or large volume, the integration is just given by the saddle point of the potential. And we find that the partition function is given as the exponential of the effective potential evaluated at the minimum plus corrections that go only as the logarithm of the volume of the cylinder. To get an idea of what some of these concepts mean, it is a good starting point to first completely ignore the fluctuations and see where we get out of this, and then eventually sort of include fluctuations consistently. Ignoring the fluctuations completely is a very drastic approximation, but it is actually not as bad as expected in capturing some of the correct physics. If we simply ignore the fluctuations, all we have is the partition function being an integral over the mean field of the exponent of minus the mean field action. Since the phi bar part of the field is a constant, the kinetic term does not contribute, and we find that the action is simply given as the integral over just the potential part, because the derivative of a constant is just zero. So we find that the action is just beta v times the classical potential evaluated at the mean field, and we can evaluate that in a straightforward way. So we find that within this mean field approximation, the partition function in the mean field approximation is given as the integral over e to the minus beta v potential evaluated at that mean field value of the field, where v of phi bar is just a classical potential. If you compare this expression for the mean field partition function to that of the partition function where we have made no approximation, let's quickly go back to 1870. This is the partition function without any approximation. We find that within the mean field approximation, the effective potential is just given as the classical potential. The classical potential has a minimum located at phi bar is plus minus m over 2 square root of lambda. So we find that if we plug this into the mean field and evaluate the path integral, evaluate the regular integral over phi bar using a saddle point, we find that the mean field partition function is just given by this result here in the large volume limit. We can also consider expectation values of the field itself. So an expectation value of the field using the full action S rather than just the free action is given as the path integral e to the minus s of phi over z. In the mean field approximation, all of these are just given by the integration over the mean field and the mean field action. So we find that this integral here is nothing else but the mean field itself. And because the mean field expectation value for saddle point is just the minimum, we find that this is the expectation value for the one-point function. In previous lectures, recall that we found that when we have a very high temperature, we can ignore the mass scale. So since the expectation value of the field is proportional to mass scale, we expect that at very high temperatures, we can actually ignore the mass. So we can set the mass to 0, if you will. So we expect that at very high temperature, what we find is that the expectation value of the field is just 0. So we conclude that in between the 0 temperature case, where the expectation value of the field is non-zero, and the high temperature case, where the field expectation value is 0, there must be some sort of transition. We call this a thermal phase transition. And we find that the expectation value of the field using the full action is an order parameter for this transition. And this concludes the present lecture.